Voyager 1 is currently the most distant human-made object, traveling through interstellar space more than 25 billion kilometers from Earth. It has been traveling for nearly half a century, yet it is still communicating with NASA and returning scientific measurements from a region no spacecraft had ever explored before. Voyager 1 began its journey on September 5, 1977, originally designed to study Jupiter and Saturn, but its mission eventually became something much larger, a journey beyond the Sun's protective bubble and into the space between the stars. Voyager 1 was launched during a rare alignment of the outer planets that allowed the spacecraft to use their gravity to accelerate and redirect its trajectory. It reached Jupiter in 1979 and Saturn in 1980, sending back images and measurements that transformed our understanding of both planets. At Jupiter, it discovered two new moons, Thebe and Metis, and found a previously unknown ring. At Saturn, it discovered new moons and rings, while its observations of Titan revealed an atmosphere so dense and complex that the spacecraft's trajectory was redirected specifically to study it more closely. After Saturn, Voyager 1 was placed on a trajectory that would take it away from the planets and eventually toward the outer boundary of the Sun's influence. The boundary Voyager 1 eventually reached is known as the heliopause. The Sun continuously releases a stream of electrically charged particles called the solar wind, creating an enormous bubble around the solar system, known as the heliosphere. Inside this bubble, the environment is dominated by particles and magnetic fields originating from the Sun. Outside it lies the interstellar medium, the extremely thin mixture of gas, dust, magnetic fields, and energetic particles occupying the space between stars. On August 25, 2012, Voyager 1 crossed the heliopause and became the first human-made object to enter interstellar space. Voyager did not simply cross a visible boundary. There was no wall, no sudden change in color, and no marker in space announcing that the spacecraft had arrived. Scientists had to recognize the transition through changes in the particles and magnetic environment surrounding the spacecraft. Voyager's instruments detected a sharp increase in cosmic rays arriving from outside the heliosphere and a decrease in particles originating within the Sun's influence. Because Voyager 1's original plasma instrument had stopped working decades earlier, scientists needed another way to directly measure the surrounding plasma. The crucial evidence came from Voyager's plasma wave instrument, which detected oscillations in the plasma around the spacecraft. The frequency of those oscillations revealed that the plasma density was far greater than in the outer heliosphere, providing strong evidence that Voyager had entered interstellar space. What Voyager found there was not the completely empty void scientists might imagine when they think about the space between stars. Interstellar space contains plasma, magnetic fields, cosmic rays, and waves moving through an extremely thin environment. Voyager 1 has been measuring these conditions directly, giving scientists information about the local interstellar medium that cannot be obtained from telescopes alone. One particularly important discovery came from the spacecraft's plasma wave instrument, which detected a faint, nearly continuous signal that scientists could use to estimate the density of electrons around the spacecraft. The signal is weak, but it changes in frequency as the density of the surrounding plasma changes. That discovery revealed something surprisingly complex. The space immediately outside the heliosphere is not completely detached from the Sun. Voyager detected changes in the interstellar environment that are influenced by disturbances originating from our own star. When the Sun produces enormous eruptions, such as coronal mass ejections, the resulting shock waves can eventually propagate outward and disturb the plasma surrounding Voyager. These disturbances can cause the plasma around the spacecraft to oscillate, allowing Voyager to effectively measure the density of the interstellar medium across enormous distances. Voyager has also helped scientists understand that the heliopause is more complicated than a simple spherical boundary. The heliosphere is moving through the interstellar medium as the Sun travels around the Milky Way, and the interaction between the solar wind and the surrounding interstellar material creates a constantly changing boundary. Voyager 1's measurements showed that the magnetic field just outside the heliopause was still being influenced by the solar wind. The spacecraft was technically in interstellar space, but the region immediately around it was still not completely untouched by the Sun. This makes Voyager's journey especially interesting because it is measuring a transition between two environments, rather than simply crossing from one place to another. Inside the heliosphere, the Sun dominates the plasma and magnetic environment. Outside it, the interstellar medium becomes increasingly important. Voyager is helping scientists understand how those two environments interact, and where the influence of one finally gives way to the other. The spacecraft has also revealed that interstellar space is far more dynamic than a completely empty vacuum. Waves pass through the plasma around Voyager, including disturbances produced by solar activity and larger structures generated by processes elsewhere in the galaxy. These waves allow scientists to study properties of the interstellar medium, such as its density and structure. In this sense, Voyager is not simply traveling through space, it is continuously taking measurements of the environment through which it travels. And Voyager's discoveries did not begin when it entered interstellar space. Some of the most important observations happened much closer to the Sun. At Jupiter, Voyager 1 discovered that the giant planet has a faint ring system, something that had not been observed before. It also discovered volcanic activity on Io, Jupiter's innermost large moon. Voyager's images showed active volcanoes erupting from its surface, making Io the first world beyond Earth where active volcanism was directly observed. The discovery transformed scientists' understanding of moons, showing that they could remain geologically active despite their small size. At Saturn, Voyager 1 discovered new moons and rings, and studied the planet's atmosphere and magnetosphere. But its encounter with Titan was particularly important. Titan is the largest moon of Saturn, and possesses a thick atmosphere dominated by nitrogen, making it the only moon in the solar system with a substantial atmosphere. Voyager 1's observations helped demonstrate how unusual Titan really is, and provided some of the foundation for later missions, including NASA's Cassini and Huygens missions. Voyager 1 also carries something that has become almost as famous as its scientific discoveries, the Golden Record. Attribution to the spacecraft is a 30-centimeter gold-plated copper disc containing greetings in 55 languages, sounds from Earth, music, photographs, and information about humanity and our planet. The record was designed as a message to any potential recipient that might encounter the spacecraft in the distant future. It contains images and instructions intended to communicate information about Earth and the humans who build Voyager. The most remarkable part is that Voyager was never designed to survive for this long. It launched in 1977, at a time when many of the technologies inside it were completely different from modern spacecraft. Its computers are extraordinarily primitive by today's standards, with memory measured in kilobytes rather than gigabytes. Yet its engineering was built around reliability. The spacecraft's radio transmitter is extremely weak by modern standards, but NASA's Deep Space Network can still detect its signal across the enormous distance separating Earth and Voyager. That communication itself is remarkable. A radio signal traveling at the speed of light takes many hours to cross the distance between Earth and Voyager 1. When NASA sends a command, the spacecraft does not receive it instantly. The instructions must cross billions of kilometers of space, and the response takes hours to return. Mission engineers therefore have to plan carefully, test commands extensively, and account for the fact that any problem cannot be corrected immediately. And Voyager 1 is slowly running out of the energy required to continue doing this. The spacecraft generates electricity using radioisotope thermoelectric generators, which convert the heat produced by the natural radioactive decay of plutonium into electrical power. But the generators lose a small amount of available power every year. As that supply declines, engineers have had to turn off instruments and other systems, one by one, to extend the mission as long as possible. NASA shut down Voyager 1's low-energy charged particle instrument in April 2026 as part of this power management strategy. The spacecraft continues operating with a shrinking energy budget. There will eventually come a point when Voyager can no longer maintain communication with Earth. Even then, the spacecraft itself will continue traveling outward. It will not suddenly stop when NASA can no longer hear from it. They will simply become silent, carrying the Golden Record and the physical evidence of a civilization that existed on a small planet around an ordinary star.
Before that happens, however, Voyager still has something important to tell us. It is currently the most distant human-made object, and NASA continues to use its remaining instruments to study the magnetic field, charged particles, cosmic rays, and plasma waves in interstellar space. Voyager 1 and Voyager 2 remain the only spacecraft ever to operate beyond the heliosphere. The destination beyond Voyager is not another planet or another star. It is the interstellar medium itself, the vast environment between the stars that surrounds every stellar system in the galaxy. Voyager 1 will continue moving through this region long after its scientific instruments stop working. In roughly the next 40,000 years, NASA estimates Voyager 1 will pass within about 1.6 light-years of the star AC plus 793888, although the spacecraft will not be traveling toward the star itself in any practical sense. It will continue on its trajectory through the galaxy. Voyager 1 has already traveled farther than any human-built object in history, yet the distance it has covered is still tiny compared with the scale of the galaxy. The Milky Way is about 100,000 light-years across, while Voyager has traveled only a few light days in terms of light travel distance. On the scale of the galaxy, the spacecraft has barely left our neighborhood. Voyager 1 has entered a region no human being has ever visited. Every measurement it sends back is a direct sample of an environment that cannot be studied from Earth in the same way. The spacecraft is slowly becoming quieter, its power supply is fading, and its instruments are being switched off one by one. But for almost half a century, Voyager 1 has continued moving outward, carrying a small piece of Earth into a part of the universe we had never reached before.